Hello everyone, this video is going to cover section 7.8, which is called proper integrals. Now, in terms of integration techniques, there is nothing new. You should be able to integrate every single integral here with all the methods from 7.1, 7.2, 3, or 4. The only thing new here is we're going to categorize this into two types. Type 1, which is going to be called infinite intervals, and type 2 will be discontinuous. So that's the only difference. For example, if I ask you to do this, which is one of the integrals I call the basic integrals, the integral for this, if you use substitution, is minus e to the minus x plus c, and that's it. Or you can do a definite integral. Let's say the limits are from 0 to 1. Notice that the integral doesn't change. This is still minus e to the minus x. But if we plug the limits, now we will get e to the minus 1 minus e to the 0. Remember that anything to the 0 power is 1. So this will be 1 minus e to the minus 1, or 1 minus 1 over e. Okay, so we have done this multiple times. The difference is going to be that for type 1, the limits of integration can go all the way to infinity. And to properly handle this, we're going to use limits. This is what I mean. This is going to be equals to the limit as b goes to infinity of the integral from 0 to b of e to the minus x dx. So notice that this is identical to this, actually to this one. So you take the integral the same way we did before, but now you have to take a limit at the end. So the integral, we already know it was minus e to the minus x from 0 to b. So therefore this will be the limit as b goes to infinity. So then you plug the limits of integration, this will be minus e to the minus b, and then minus e to the minus 0, which we already say was equals to 1. So notice that the integral is the same as this one, it hasn't changed. So this is the same thing as the limit as b goes to infinity of 1 minus e to the minus b. And remember that as b goes to infinity, this will equals to 0. So this is 1 minus 0, which is just 1. So the integral is 1. Now it is very useful to see this in a graphical form. E to the minus x, you remember the graph looks like this. So this is e to the minus x. And this is telling you that this total area from here all the way to infinity is just equals to 1. So therefore this integral is going to be called convergent. We're going to talk about a lot of convergence later in the class. But convergent just means that the limit or the integral is finite. By finite, it just means it's not equals to infinity. Okay. Right, let's try the next one. Remember that this is the same thing as the integral from 1 to infinity of x to the negative 2 dx. And because of the limit of integration is infinity, this is going to be the limit as b goes to infinity. By the way, there is nothing special about b. You can pick any variable except x, so you don't get confused. Or the integral from 0 to b of x to the minus 2 dx, which will be the limit as b goes to infinity. Remember that the integral of x to the minus 2 is equals to x to the minus 2 plus 1, minus 2 plus 1, which is technically just 1 over x, or minus x to the negative 1. Okay, so therefore this will be minus x to the negative 1 from 0 to b, sorry, 1 to b, So in this case, this will be the limit as b goes to infinity of minus, this will be b to the negative 1 minus 1 to the negative 1, which in this case it will be just the limit as b goes to infinity of 1 minus 1 over b. And again, notice that this goes to 0 as b goes to infinity in a similar way as this one. It's not the same problem, but very similar. And again, this equals to 1. So one more time, from the graphical point of view, the graph of 1 over x squared looks like this. And if you go from 1 to infinity, this area is also finite. So that means that this interval is also convergent. Okay? By the way, not all intervals are convergent, like you will see in the next one. Before I do this example, let me do one case where the interval is not convergent, which means it will be divergent. And this example is going to be very useful once we get to chapter 11. So let's say you want to integrate just the x over x from 1 to infinity. So everybody should know that the integral of the x over x is ln x. So if we go with the limits, this will be the limit as b goes to infinity of the integral from 1 to b of the x over x, which will be the limit as b goes to infinity of ln x from 1 to b. So notice that this is the limit as b goes to infinity of ln b minus ln of 1. Notice that ln of 1 is equals to 0, so you don't really have to worry about that. But the limit as b goes to infinity of ln of v is infinity. So therefore this is not convergent, so this is actually divergent. So this example is going to be very, very important later, so make sure you make a note of this. And more importantly, if you look to the graph of 1 over x, remember the graph of 1 over x is very similar to 1 over x squared. But this one is telling you that from 1 to infinity, that this area is infinite, while for x squared is finite. Okay, so this result is going to be very useful later. Now this question looks different than the previous one, not this one, the previous one we did, but it's essentially the same once you do a substitution. Here, let's say that u is equals to ln x, so therefore the u will be the x over x. Okay, so notice that this is the same thing as the integral of du. The du includes this x right here, and then this will be u squared. Okay. Now you have to change the limits of integration. Notice that x goes from e and also to infinity. So since u is equals to ln x, how much is ln of u? Well, ln of u will be, sorry, ln of v is 1, and ln of infinity is infinity. So essentially this is the integral from 1 to infinity, and this is the exact same integral we did right now. Remember, this was the limit as b goes to infinity from 1 to infinity u to the negative 2 du, and we end there with 1. You should check this is the exact same thing we did in the previous example, which again, this is convergent. So if the limit or if the integral is less than infinity, it's going to be called convergent. All right, so now let's do another example of an infinite limit. Now there are several ways in which you can do this problem. You can use trig substitution, but probably the easiest way is to do just a basis substitution. So let's say that u is equals to x squared. So then the u will be to x dx. Okay. And also here we have the x. The limits for x are 0 and infinity. So that means that u will be 0 squared, which is just 0. And then infinity squared is just infinity. So the limits don't change. So therefore this becomes the integral from 0 to infinity of du over u squared plus 1, which this is one of the basic integrals. So this is the limit as b goes to infinity with the integral from 0 to b of the u over u squared plus 1, which should be the limit as b goes to infinity or tangent inverse of u, and this is from 0 to b. So therefore this is equals to the limit as b goes to infinity of tangent inverse of b minus tangent inverse of 0. Now if you forget this from trigonometry, just to refresh your memory, recall this, that tangent of pi over 2 is equals to infinity in terms of limits. So that means that tangent inverse of infinity has to be pi over 2. Okay, so this is also a pretty useful result to remember for the rest of the class. Also remember the tangent of 0 is equals to 0, which means that tangent inverse of 0 is 0. So in our case, this limit, therefore, because of this, has to be pi over 2. Let me simplify this. Let me fix that. So this limit will give you pi over 2, and this limit is 0, so the answer is pi over 2. That's it. Right, so finally, let's look to type 2. This should be type 2, not type 1. So type 2. And that's the case where there's this continuous integrals. Again, if you get rid of this is the usual integrals that you had to do before. And by that I mean this. If I just ask you to integrate this, the x over 1 minus x squared, everybody should know that that's sine inverse plus c. And that's it. Again, notice that the difference between this integral and this one are just the limits of integration. But in this particular case, if you look closely to the number 1, 1 squared is 1 and 1 minus 1 is 0. So you're dividing by 0. And remember, that's one of the two things you cannot do in math. So that's what makes this an improper integral. So therefore, you have to use limits when you integrate. So this is going to be equals to the limit as b goes to 1 or the integral from 0 to b of dx over 1 minus x squared. Also, you have to be aware of this continuity, like how is this happening. Notice that if you are approaching to 1, you cannot come from the right side. Why? Because this will be more than 1. More than 1 will give you a negative number here, which it doesn't exist. So therefore, you have to approach 1 from the left side. So you say 1 from the left side, okay? And we did one-sided limits at the very beginning of the class. We already know what the integral is. The integral is this. So this is equals to the limit as b goes to 1 from the left side of sine inverse x. Okay, then plug the limits of integration, which is from 0 to b. So this will give you the limit as b goes to 1 from the left side. And now this will be sine inverse of b minus sine inverse of 0. And just like we did with tangent, remember that sine of 0 is equals to 0. So that means the sine inverse of 0 is also equals to 0. Also notice that sine of pi over 2 is equals to 1. That means the sine inverse of 1 has to be pi over 2. So therefore this will be again pi over 2 minus 0, and the answer is again pi over 2. It doesn't mean whenever you have sine inverse or tangent inverse that the answer is always 1. It just happens to be there. Alright, so let's do one last example of this. Notice here that the issue is going to happen at 2 because you're going to divide by 0. So therefore this one you have to break the intervals into two parts, 0 to 2 of x over x minus 2 dx, and then the integral from 2 to 5 of x over x minus 2 dx. So for one you're going to approach from the left side and the other one from the right side. Now before we do the limits, notice that to integrate this you can use partial fractions. You can divide here, or you can do the trick that I showed you before. This is the same thing as x minus 2 plus 2 over x minus 2. Remember, you can always add nothing to anything and you still have the same thing. The only reason why we did that is because this gives you 1. Well, let me write it like this. This is the same thing as just doing the long division. This is just a fancy way to do it. Notice that this is equals to 1 plus 2 over x minus 2. So therefore the integral of this with the integral of this, which will be x plus 2 ln of x minus 2. Okay. So therefore for this one, this will be the limit as b goes to 2 from the left side of x plus 2 ln x minus 2 from 0 to b, plus the limit, and you can use b again, but I'm just going to use a different letter. Let's say t goes to 2 from the right side. The integral is still the same, it hasn't changed. And this is from t now to 5. Alright, so for the first part, for this one, if you plug in b, well, the first one will be 2, that's not an issue. And then this is 2 ln. But as x is approaching to 2 from the left side, this is going to go to minus infinity. So this is approaching ln of 0, which is infinity. And if one of them fail, that's enough for you to say that the limit doesn't exist. And also notice that this is why we have the absolute value. The 0 will be okay, but 2 minus 2 will give you 0. And you notice the graph of ln x look like this. So notice as you are approaching 2 or 0 from the left side, you cannot even get that, but it's going to minus infinity. You can approach 0 from the right side, but it still will get to minus infinity. So this will also give you, this actually give you minus infinity. So this is an example of also a divergent, because it doesn't converge to anything. It goes to infinity. Well, this one is a convergent because it approaches to pi over 2. Now, so just to recap, when it comes to integration, it doesn't change anything in terms of techniques. Are the same techniques from 7.1 to 7.4. The only difference is the limits can go to infinity, or you may have a discontinuity. You have to deal with them this way. But in terms of integrating, there's nothing new. All right, that's it.